1.5 is infinite geometric series. So we've done geometric series. That's just when you add up a geometric sequence. By definition, then, the word infinite means something that goes on or continues. So an infinite geometric series, then, is a series that continues on forever. It does not have a final term. So what we were looking at in our last ones in arithmetic and geometric, we were always looking at a final term. Our series ended somewhere. With an infinite one, you don't have that final term. We're saying that this goes on. So it says, consider the infinite geometric series that has term 1 is 4 and a ratio of a half. Write the series up to 13 terms and then find the sum for sum of the 5, sum of 7, 9, 11, and 13. So I didn't leave a whole lot of space for this, so we're going to have to write kind of small. So if we're looking at term 1, we have 4 plus, term 2 is half of that, so it'll be 2 plus 1 plus 1/2 plus 1/4 plus 1/8 plus 1/16 1/32 plus 1/64 plus 1/128 plus 1/256 plus 1/512 plus 1/1024, and it'll go on and on and on. And I think I have. So I've got 1, 2, 3, 4, 5, 8, 9, 10, 11, 12, 13. So those are the first 13. So if I add these up, and you can just do this on your calculator, the sum of the first 5 terms is 7.75. If I went to the sum of the first 7 terms, so I'm adding on the next 2 after that, it equals 7.9375. Sum of the first 9 terms is 7.984375. Sum of the first 11 terms is 7.99609375. So, if I did sum of the first 13 terms, I get 7.990, well, I think I missed another 9 in there, 23438. So what do you notice about this sum? I start at 7.75, 7.9375, 7.984, 7.996, 7.999. So what's happening here is our sum is getting closer and closer and closer to 8. If I were to continue going on, my decimal number would just get longer and longer and longer, and eventually be 7.999999999, whatever. So it says when the sum approaches a fixed value, the series is said to be convergent. So if you think of converge and diverge, if you think of those two terms, converge, if you're converging, that means you're getting close to something, or you are taking two things and you're moving them closer together. If something's going to converge, then eventually it's going to come close to touching. So if you have a series and it's getting closer and closer and closer to the same number, we say that's a convergent series. So it says when this is the case, R must be between -1 and 1. So in order for a series to be convergent, then you have to have a ratio that is between -1 and 1. So it could be -1 or -0.99999, and it could be 0. It could be 0.99999. It has to be in between -1 and 1. So it says if in an infinite series each term continues to grow, the sum does not approach a fixed value. It actually approaches infinity or negative infinity. In these situations, r is less than -1 or it's going to be greater than -1. So when you have a case where your number, when you're doing your sum and your sum keeps growing, either growing in the positive side or growing in, or shrinking, I guess, if you think of it, because as your numbers increase in the negative, your value is actually less. So if that happens, then your infinite series is said to be convergent. So it's either moving way off into the negatives or way off into the positives. R needs to be, in that case, either less than -1, so -1.1, or -1,000,001, or it has to be greater than 1. So for a series to be infinitely convergent, so remember, convergent means it's getting closer to 1. The formula that we use for that is the sum in this little sideways 8 means infinity. So the sum to infinity is equal to term 1 divided by 1 minus r. So T1 is your term, and R is your common ratio, and S with the symbol is the sum of an infinite number of terms. So we're going to use this formula to find the sum from our example at the top of the page. So my term 1 was equal to 4. My ratio was equal to 1/2. My formula for the infinite terms, sum of the infinite terms, is T1 over 1 minus r. So this is 4 divided by 1 minus 1/2. So this is the same as saying 4 divided by 1/2, which is the same as 4 times 2, which is 8, which is what we found by doing the actual adding of those. Okay. Examples to do: determine whether each infinite geometric series converges or diverges. Calculate the sum if it's other than infinity. So, first thing you have to do then to decide if it is convergent or divergent is that you have to calculate the ratio. So for A, my ratio is equal to 1/5 divided by 1, so it's just 1/5. My term 1 is equal to 1. So if my ratio is 1/5, that means that it's in between -1 and 1. So this is a infinite convergent series. So since it's an infinite convergent series, I can find the sum of this. So the sum of the infinite terms is equal to term 1 over 1 minus r. So it is 1 divided by 1/5, which is the same as saying 1 times 5. So my answer here is, oh, sorry, I wrote that down wrong. 1 minus 1/5. I'll just continue it here. So that's equal to 1 divided by 4/5, which is the same as saying 1 times 5 over 4, which equals 1.25. So my sum would eventually get close to 1.25. So B, 4 minus 8 plus 16 minus 32. So the first thing I need to do is calculate my ratio. So I have term 2 is -8 divided by term 1, which is 4. That equals -2. So that means that my R is going to be less than -1. So this means that this is a divergent series. So it will go on forever. I wouldn't be able to actually find the sum. So next example, it says you can express 0.584 with the bar over top as 0.584584 or 0.584 if you want to express it as a sum, plus 0.00584 plus 0.0000, and I'm just going to write this in here, 584, and so on. So we would just keep adding zeros, 3 zeros, and then putting 584, 3 more zeros, and 584. So it says determine the sum of this series. So in order to do that, you have to take a look at our expansion here. So you have to take a look at the series and figure out your two terms, or your two variables. Term 1 is equal to 0.584. My ratio in this one is going to equal term 2 divided by term 1. So my ratio for that is then going to be 0.001. So that because it's between -1 and 1, then this is an infinite convergent series. So that means that I can then use my formula, my infinite sum, or sum of infinite numbers, formula. So that's term 1 over 1 minus r, and find out what sum this would get close to. So term 1 was 0.584. I divide that by 1 minus 0.01, which equals 0.584 divided by 0.999, and that equals 0.584, 584, 584, so we just put the bar over top. Okay, the last page here is just basically a summary page. So some things to keep in mind when you're working with convergent and divergent series. So in a geometric sequence, if the absolute value of r is less than 1, then it converges on 0. So it gets closer to 0. So if your r is less than 1, but greater than 0, so between that 0 and 1, then your sum is going to get closer to 0. If r is greater than 1, then you're going to have a divergent series. So for the first one, you'll be able to find a sum that it's getting closer to. And in the other case where it's greater than 1, you're not going to be able to find the sum. So in an arithmetic sequence, if d is not equal to 0, then divergent to positive or negative infinity. So if you can find the sums for arithmetic sequences that go on forever, or infinite ones. So if your common difference is not equal to 0, then it's considered to be divergent, and it'll either go to positive infinity if d was positive, and it'll go to negative infinity if your d was negative. So the nth term is equal to 2n over n plus 1. If the degrees of n are equal, then the sequence converges to the ratio of the leading coefficients. So basically what that's saying is if you're doing an equation that's got say squareds in it, like 2x squared and then 4x squared, 6x squared, and so on, then if the degrees of each of the numbers are equal, then your sequence is going to converge to the ratio of the leading coefficients. So if it was a 2 was your leading coefficient, then it would be a 2. We're not going to come across number 3 very long. If you are working, if Tn is equal to n squared over n plus 1, if the degree in the numerator is greater than in the denominator, then the sequence diverges. So it means you won't be able to have a sum. It'll go on forever. If the degree in the numerator is less than the degree in the denominator, then your sequence is going to converge to 0. So if you have, for these three here, basically, what it's saying is if you have questions like, well, even if it was tn over n plus 1, then your next term would be tn minus 1 times n plus 1 minus 1. So it's going to go on forever and ever and ever. So if you have ones that are set up as kind of equations like this, then those three rules will apply. If your degrees in the top and the bottom are the same, then your sequence is going to converge to whatever the ratio of those coefficients was. If your numerator is greater than the denominator degree, then you're going to have a divergent, can't find the sum. If the numerator is smaller than the denominator degree, then the sequence is going to get close to 0. It says if the sequence bounces between two values, it is divergent. So if your sequence is going in between, say, 2 and 4, 2 and 4, 2 and 4, you're not going to be able to find the sum of that. It's going to go on forever. So your assignment there is on page 63, number 1. I don't have to repeat it. You can read it yourselves.